We've laid out the theory for cubic spline interpolation. Now it's time to see how we'd set up the equations in order to solve for the polynomial coefficients. Let's first focus on working out some of the details of that cubic function. What are the values and derivatives of a cubic of this form? Well, taking the derivative gives that, taking the second derivative gives that expression, and taking the third derivative finally gives a constant. It makes sense. A cubic has a constant third derivative. We can stack those in a vector and express this as a matrix vector multiply, where the matrix depends on the value of x and its square and cube, and the vector consists of the coefficients of the polynomial. This will be a useful way for us to express it, since it's the coefficients that we're trying to solve for. Let's be more specific and think about our polynomial f sub k. We'll write f sub k relative to the left endpoint of the interval where it's defined. It's defined on the interval xk to xk plus 1. So write fk as shown there. The derivatives are as you'd expect. And then let's evaluate fk and its derivatives at the two endpoints that it's interesting to evaluate it at xk, in which case we get a very simple expression, as well as at xk plus 1, the right endpoint. Let's use hk to represent the difference between xk plus 1 and xk, and then the expression for f and its derivatives at the right endpoints takes on that form. It's easy to see how these are both obtained. In one case, we're plugging in xk for x, and all the x terms vanish. In the other case, we're plugging in xk plus 1 for x, and all of those differences become hk. Hk raised to various powers, multiplying the various coefficients of a. Remember that all of the constraints we're imposing involve conditions on fk and its derivatives at the left endpoint xk and the right endpoint xk plus 1. Therefore, these formulas will be very useful in building up the constraints in a concise manner. Let's see how that's done. The first constraint was at x1. f1 at x1 should be y1. Remember that f1 at x1 is simply a0 associated with the first polynomial. I'm writing the coefficients of the first polynomial as a0, a1, a2, a3 with a subscript 1 on the outside to integrate first polynomial. So there's the first constraint. It tells us that a0, 1 is y1 in fact. What about at the intermediate points? Remember the conditions. The k minus 1th polynomial at xk should be yk. The kth polynomial at xk should be yk. And the slopes should be equal, and the second derivative should be equal. These clearly involve the coefficients associated with the k minus 1th polynomial and the coefficients associated with the kth polynomial. Let's write them out. Here on the right, we see the coefficients associated with the k minus 1th and the coefficients associated with the kth. Each row in this matrix vector multiplication represents one of these constraints. The first row is exactly the value of the k minus 1th polynomial at xk. It involves the k minus 1th coefficients and nothing times the kth coefficients, and it must equal yk. The second row is the value of the kth function at xk, and it only involves the kth coefficients. And since it's the kth function at xk, we know that gives the simple expression 1 times the a0 entry. Next, we have the derivatives of the k minus 1th function. That involves hk minus 1, as well as the kth function, and that's much simpler since it's being evaluated at its left endpoint. Finally, the second derivatives, same way. The k minus 1th function involves the k minus 1th coefficients and hk minus 1. The kth function only involves its second coefficient. Since those have to be equal, we've actually subtracted them to give 0. Those four rows represent those four equations. One thing we see from that is it always implies that the a0 entry of the kth set of coefficients is always equal to yk. Finally, at the right endpoint, the n minus 1th function at xn should equal yn. This takes on the form involving the coefficients of the n minus 1th polynomial and the appropriate powers of h multiplying them. Remember that in addition to establishing all the constraints, we've also solved for the a0 term in every one of the polynomial coefficients. It's always equal to the y data of that associated interval. a01 equals y1, a0k equals yk for k equal 2 up to n minus 1. And there are only n minus 1 polynomials. So we've always solved for the a0. So let's go through what we know. Up here, this a0 is actually known to be y n minus 1. This a0 is yk minus 1, and this a0 is yk. Those are data, those are not unknowns. We can make those substitutions and move those corresponding values to the other side of the equation, keeping only the unknowns a1, a2, a3 on the left-hand side. I need you to get out a piece of scratch paper, and for those two expressions, do that. The resulting equations will have fewer unknowns. Up here, there'll only be 3 unknowns, and down here, there'll only be 6 unknowns. Down here also, we can eliminate one of these equations. The second equation is just exactly the expression that said a0k equaled yk. We're using that equation to eliminate a0k, so we don't need to write it anymore. So this will also only result in 3 equations. If you do that carefully on a piece of scratch paper, it will only take you a few minutes, and you should get the equations that we'll present on the next slide. Please do that now.